Alright, we're going to continue 5.4 part 2, and we're going to look at the medians and in a triangle and applying this. We did number 1 together. I'm going to give you the opportunity to pause the video, and you could do number 2 and 3 on your own and then press play to check your answers. Okay, so let's look at number 2. We want to find TC and BC. They tell us BT is 1,000 feet. So TC and BC, T is a midpoint. So since T is a midpoint, obviously BT is congruent to TC. They tell us in number 2 that BT is 1,000. So this piece here is 1,000. Well, if these pieces are congruent, then TC is also 1,000 because T is the midpoint. If both pieces are 1,000, then BC is 2,000. Now, number 3, we have to find PA and TA, so we have to do a little more work for that one. PA and TA, we need the 2 pieces of the median. Now, the bigger piece is always 2/3 of the whole thing. So PA is 2/3 of TA. But we don't know what the whole thing is. But they do give us that PT is 800. So this little piece here is 800. Well, if this longer piece is 2/3, then the little piece is obviously 1/3. So PT is 1/3 the whole thing. PT is 800. So to find TA, we have to cancel the fraction, and you do that by multiplying both sides by the reciprocal. So you multiply both sides by 3/1. The fractions cancel, and you get TA is equal to 800 times 3/1, which is 2,400. So we found TA, 2,400. Now PA is 2/3 of TA, so we have to plug that 2,400 in. So 2/3 times 2,400. We can put that into the calculator. $2,400 times 2 divided by 3 gives us 1,600. So PA is 1,600. If you weren't sure what I did on the calculator, I did 2,400 because it's a whole number times the numerator, 2 divided by 3, because you could do 2,400 over 1. 2 times 2,400 is 4,800 divided by 3, and that'll give us 1,600. Okay, now we've gone over medians. Now we're going to go over altitudes. An altitude of a triangle is the perpendicular segment from the vertex to the opposite side or to the line that contains the opposite side. So if you look at this triangle QPR, from Q, if you just go straight down and make it perpendicular to the side that it's opposite, that Q is opposite from, that is the altitude. It's different from median because median is a vertex that goes straight down to the midpoint. So if we were to draw a median here, it would go from Q to about the middle. It could be close, but it's not the same. So from Q down to the midpoint. So it's a little bit different, the median and the altitude. The altitude does not necessarily go to the midpoint. The median for sure goes to the midpoint. Okay, an altitude could be inside of a triangle or it could be outside of a triangle. In this case, if you draw a line straight from Q down, you're going to notice that line is actually outside of the triangle. So an altitude does not have to be in the triangle. So if you look down here, if we name this triangle ABC, if I draw a line straight down from A and kind of make it line up with where B is, it forms a altitude, but it's not inside the triangle. Okay, here we have our next theorem. It's called concurrency of altitudes of a triangle. The lines containing the altitude of a triangle are concurrent. So, in other words, there's 3 altitudes in each triangle and they actually intersect. So if we were to name this triangle here, this acute triangle, like the one here, ABC. If we draw a line straight, make it perpendicular, another line from the vertex straight, make that perpendicular, and down from A, oops, I want to make it straighter than that. This is where the altitudes intersect. And so in this particular triangle, the concurrency is right inside the triangle. That point where all those three altitudes meet is called the orthocenter. Oops. Orthocenter. The point at which the lines containing the three altitudes of a triangle intersect at an orthocenter. Different from medians, where three medians meet is the centroid, but where three altitudes meet is the orthocenter. So example 3 asks us to find the orthocenter for an acute triangle, a right triangle, and an obtuse triangle. So I'm going to use the triangles we had on our previous slide. Now, this right triangle has a special quality. Let's draw the altitudes and you'll see what I mean. This is 90 degrees. If we take this vertex and draw a line straight down, you're going to notice that the line we draw actually coincides with the side of the triangle. So the altitude on a right triangle, this altitude actually coincides with the side of the triangle. If we have this vertex and draw a line perpendicular to the side it's opposite from, it also coincides with the side. And then if we draw from this vertex a line straight down, we have our third altitude. And these three altitudes actually meet on a vertex right here. Oops. Right here. So in a right triangle, the orthocenter is actually on the triangle. In an acute triangle like the first one, so this one was acute, the orthocenter is inside the triangle. In a right triangle, the orthocenter is on the triangle. Let's take a look at what happens with an obtuse triangle. If we draw a line straight down from this vertex, we obviously have one altitude here. Now, with this vertex, if we were to draw a line straight here, if we draw one here, there's no way it'll be perpendicular to the side it's opposite from. But if we extend this side and draw a line straight, then it is perpendicular. If we extend this side and draw a line straight from that vertex, we're going to have to extend it. It is perpendicular. And if we extend those three, we'll see that they actually meet outside of the triangle. So in an obtuse triangle, the orthocenter is actually outside of the triangle. And I'll show you some better drawings over here. So in an acute triangle, the orthocenter is inside. In a right triangle, the orthocenter is on the triangle. In an obtuse triangle, the orthocenter is outside of the triangle. Okay. Now these are some proofs that involve medians and altitudes. Here it says, prove that the median of the base of an isosceles triangle is an altitude. So we want to show that this median is actually also an altitude. Triangle ABC is isosceles with base AC. BD is the median to base AC. Prove that BD is an altitude. Alright, so we're going to have to use several things that we've learned throughout the chapters. First of all, for this to be an altitude, it has to be perpendicular. We don't know yet if it's perpendicular. We have to prove that it's perpendicular. So think about what we can prove so far. What I see here is two different triangles. where AB is congruent to BC, AD is congruent to DC. BD is congruent to itself by reflexive property. So I see two triangles congruent by SSS property. Triangle ABD is congruent to triangle CBD by SSS. Now, because the triangles are congruent, we can say that the angles are, the corresponding angles are congruent by CPCTC. So these two are congruent. Now, D is a midpoint, so that means, let me open this up. These two are congruent, and they are also a linear pair. Since they're a linear pair, and they're congruent, by definition, they have to be 90 degrees. Since these are 90 degrees, we can say BD is an altitude. Perfect. And this is a guided practice that you'll try on your own. And that's it for this section.